Alright, section 10.3 is on page 600, talks about the integral test. The integral test is nothing more than our traditional integration. There is a couple of properties you need to look at. Let this be a sequence, positive terms. So they're talking about this. They want this to have positive terms. Suppose a sub n equal f sub n, where this a sub n is continuous. Just make sure it is continuous. Positive, make sure it's positive. Decreasing is a different story. We're going to make a deal, me and you. If n only appears in the denominator, you could simply say decreasing, me and you have no problem. If n doesn't appear only in the denominator, then you're going to figure out where's f decreasing by taking a derivative, set it equal to 0 where it does not exist, and working the first derivative test. Wherever the derivative is negative, this f of n, which is a sub n, is decreasing. So you figure out where that happens, and you tell me from that point on. So, those three must be satisfied. The sequence part of the series must be positive, decreasing, and continuous. Then, instead of doing this integral from capital N, which I'm going to find if there's a need, to infinity, I'll simply take the integral from n to infinity. That's like the improper integrals that we did in section 8.8, except they're always continuous. You just have to worry about the infinite part, and therefore identical to what we did in 8.8, and we're talking about this case. Always this case. And there it is. That's really what this section is about. Now, you take that limit, that integral. If that integral converge, then the series converge. If that limit diverge, then the series diverge. So, number 1 through 12, again, on a test, I will never specify what to use. I'll simply say, does this series converge or diverge? So if I'm looking at page 604, number 1 through 12, it says specifically use the integral test. So every time you want to use the integral test, you want to ensure that this is a sub n. It didn't register. You want to say that's positive, make sure it's positive. Continuous, you just have to say that. Now, the decreasing part. I will accept decreasing if n only appears in the denominator. You don't have to do any work. And then what? Now you're looking at the integral from 1 to infinity of 1 over x to the 0.2 dx. That is the integral of x to the negative 0.2 dx. Add 1 to the power, divide by that. And just like we did, I allowed you to do in section 8.8, this is 0.8 over 0.8. Now you introduce the limit. So you ignore the limits on the integral, just integrate first, get that out of the way. Then this is going to be the limit as t approaches infinity of 1 over 0.8 into t. By the way, this is 0.8 is 8 over 10, which is 4 over 5. So this is really the fifth root of t to the fourth minus 1. As t approaches infinity, doesn't this approach infinity? So if this is infinity, what does that mean? Therefore, this series diverge by the integral test. And there it is. Anytime you quote the integral test, I need to see that you satisfied those three. How about this problem? Number 4. Well, again, if I really glance at this, okay, even better. If I glance at this, I would say that is positive. You're right. It's always positive for n equal 1. It's continuous. It's not continuous at n equal negative 4, but n starts at 1. And you could just say decreasing, that's acceptable if n only appears in the denominator. If it doesn't, you have to show that. And now what? Now I'm going to look at the integral from 1 to infinity of 1 over x plus 4 dx. That is a natural log of x plus 4. No need for absolute value. because on this interval, this is always positive. Limit as t approaches infinity, isn't that natural log of t plus 4 minus natural log of 5? As t approaches infinity, this will approach infinity, so that would be infinity, therefore diverge by the interval test. If you say converge, you have to tell me by what? If you say diverge, you have to tell me by what? And I added an example. So I could say this is positive, you're right, decreasing, you're right, continuous, you're right. Well, what's the integral of 1 over x squared dx from 1 to infinity? Oh, I messed up. I messed up big time. I'm sorry. I meant to write infinity. Where's infinity? Okay. So, now what? This is really negative 1 over x evaluated from 1 to t, taking the limit as t approaches infinity. Again, this is x to the negative 2, add 1 to the power, divide by that. So that's going to be the limit as t approaches infinity of negative 1 over t plus 1 over 1. Well, that's going to approach 0. That's going to be 1. Therefore, this converge by the interval test. So if I look at those three problems, I look at if n is bigger than, if the power is bigger than 1, and I integrate, 3, 4, 5, doesn't that mean that x is going to remain in the denominator after you integrate? And doesn't that mean that this portion will always be 0, and therefore it will converge? And if this power is less than 1, then, say you're looking at the integral of 1 over x to the less than 1, say negative 3. Isn't that really the integral of x cubed dx? Isn't that x to the 4 over 4? And the limit as t approaches infinity, that's going to diverge. So we know that if it's bigger than 1, it converge. If it's smaller than 1, it diverge. And what if it's 1? If it's exactly 1, isn't the integral of 1 over x dx natural log of x? And if I plug in t and take the limit as t approaches infinity, doesn't that diverge? So out of this scenario, I'm able to come up with what's known as the p-series, and this is what it says. So my conclusion is that if I look at a series from I equal 1 to n of n raised to a number, if this number right here is bigger than 1, this series converge. If it's less than 1, equal to 1, it diverge. And I could refer to this as the p-series, and that is accepted all throughout. For example, here, these problems, they specifically say on numbers 1 through 12, use the integral test. On a test, I don't specify. So you could use that on number 2. You could use that on this example. You can't use that on this because there's a plus 4. You can only use it on series that look identically like this. So I look at problem number 10 next. So now we know 3 rules. I look at problem number 10 and I'm looking at that. They did say use the integral test. We have an issue. So you could say this is positive. I'll believe you. You could say it's continuous. It better be continuous. But if you want to say decreasing, well, not so fast. Why is that? Well, n appears at the top at the bottom. You have to tell me decreasing where. So if you take f of x and set it to be x minus 4 over x squared minus 2x plus 1, the derivative will be 1 times x squared minus 2x plus 1 minus x minus 4 times derivative of the denominator, the quotient will basically, all over the denominator squared. That would be x squared minus 2x plus 1, and this is 2x squared minus 4, minus 2, minus 8 is minus 10, plus 8, and there's a negative in front, so you distribute that in, and you end up with a negative 2x squared plus 10x minus 8 all over x minus 4 squared. You'll end up with a negative x squared plus 8x minus 8 over x minus 4 squared. Okay, I do see a mistake that I made. Over the denominator squared. Now the denominator, isn't this denominator really n minus 1 squared? So isn't that x minus 1 squared? That's a 4. And now what? Now I'm gonna take the top and see if I could factor it. That would be negative x squared minus 8x plus 8 over x minus 1 squared. And let me see how that works. Oh boy, I forgot a plus 1 there. So that's 1. That makes this a negative 7. I'm like, wait a minute. That's not matching my notes. So, altogether, I'm looking at negative x minus 7 into x minus 1 over x minus 1 squared, a fourth. This cancels one of those. I'm trying to test negative x plus 7 over x minus 1 cubed. So if I do my testing, if I let x equal 1 and x equals 7, I'm not going to worry about this region. I'm going to worry about 7. Reason for that, if from 7 to infinity this series converge, adding 6 terms to it is not going to make any difference. And if from 7 to infinity this series diverge, adding 1 to the first 6 terms is not going to make a difference. So how does that work? If I pick a point to the right of 7, let's say 8, that's positive. And negative 8 plus 1 is negative. Negative over a positive is a negative. The function is decreasing. So I'm going to say from 7 to infinity. Or I could say from 8 to infinity. Because I want to include that. So I'm going to integrate from 8 to infinity x minus 4 over x minus 1 squared dx. And here I have a couple of options. I could use the trick that I mentioned students have taught me. I could say this is the integral of x minus 1 squared into x minus 1. And this will be 1 over x, that's natural log of x minus 1, minus plus 3 over x minus 1, evaluated from a to t, taking the limit as t approaches infinity. And I need a bit more space. That would be the limit as t approaches infinity of natural log, oh boy, let me fix that. T minus 1 plus 3 over t minus 1 minus natural log of 7 plus 3 over 7. Well, I know that this right here hit infinity, that hits 0. So this is going to be infinity, therefore the series diverge. Now, I'm supposed to look at the series and say, wait a minute, but this is the series from 2. Keep in mind, adding 2, running from 2. So if I take n equal 2, n equal 3, n equal 4, n equal 5, right? So a sub 2 plus a sub 3 plus a sub 4 plus a sub 5 plus a sub 6 plus a sub 7 plus the series n equal 8 to infinity of a sub n. If this diverge, adding 7 terms will not make a difference. And if this converge, adding 7 terms will not make a difference. So we'll just stick with that. That was infinity. Alright. Now, few problems to look at. 14. Here they say Determine whether the series converge or diverge. Okay, how does that work? So I take the limit as n approaches infinity. I don't have to work it out. I could do that in my head, so to speak. See if I get anything other than 0 that doesn't work here. This is the series n equal 1 to infinity. Isn't that 1 over e to the n? So isn't that geometric? And the common ratio is 1 over e in absolute value that's less than 1. Converge. Done. How about this problem? I'm going to say this is negative twice the series n equal 1 to infinity of 1 over. Isn't that n to the 3 halves? And if I look closely at this mu p series, that looks just like this. And p is 3 halves bigger than 1. And what did we conclude? If it's bigger than 1, it converge. Now, if you use the letter P, I'm assuming you're supposed to say by P series. But since we're going to only use the P series with the P with P series, no need to say that. And similarly here, by using G and R, you're telling me this geometric, so you don't have to say by geometric series. The book does, you don't have to. How about this problem? Well, if I really glance at this problem, I notice that, guess what? This limit doesn't equal 0. That's an easy way out. If I divide by the highest power term of the denominator. Limit as n approaches infinity, that's 5/4 to the n over 1 plus, that's a 0. And as n approaches infinity, this is exponential with a base bigger than 1. This is exponential growth by test for divergence. Test for divergence can only indicate whether a series can diverge or not. It can't do anything else. How about 32? Again, I noticed that this is geometric. R is 1 over natural log of 3. Now be careful with natural log. Natural log, this is 1 y equals 0. At 2.71, this is a 1. Since that's bigger than that, so this denominator is bigger than 1, then this is less than 1 for sure. Therefore, converge. That's all you have to show. If it's geometric, show me that R is less than 1 in absolute value, and you're set. And the next problem up is 36. This is something that doesn't leave you alone. It keeps you coming back. And we did that already. Let's do it again. If I take the limit as n approaches infinity of n tangent of 1 over n, that is infinity times and 0. What does that mean? I need to manipulate the problem. I'll take the limit as n approaches infinity of the tangent of 1 over n divided by 1 over n. As n approaches infinity, that's a 0 over 0. Very good. I could use L'Hopital. Limit as n approaches infinity, that will be the secant squared of 1 over n times negative 1 over n squared over negative 1 over n squared. That's the beauty of trig over angle. The angle always comes out. And as n approaches infinity, this will be 0, and the secant of 0 is 1. Doesn't equal to 0. Therefore, diverge by test for divergence. So your work has to be clear. I have to see every step and I have to see all the work. The answer gets you nothing. And if you answer and do the work and don't quote, we have a problem. How about that problem? Well, you could try anything you want. In the next section, we're going to learn about comparison test, and that turns out to be an easy way out. For now, we don't have that. So I'm thinking I'm going to use the integral test, but I have to show that's decreasing. No way around it. If I take a derivative of the top is e to the x times the bottom minus the top derivative of the denominator ten plus e to the x times e to the x all over the denominator squared. If I factor an e to the x times 10 plus e to the x out of the top, out of the first I'll have 10 plus e to the x minus, out of the second, so if I take this and one of those, this and one of those, minus 2e to the x. This cancels one of those, so I'm left with e to the x times 10 minus e to the x divided by 10 plus e to the x cubed. Let me just make sure of the math. 10, take that out, 2, yep. So what am I looking for? E to the x can never be 0. The denominator 10 plus e to the x can never equal 0. It has to be that 10 minus e to the x equals 0. That means e to the x equal 10, x equal natural log of 10. So this is f prime and this is f. This is natural log of 10. If I want to pick a point to the right of that, why don't I pick x equal natural log as a test point of e cubed? Actually, let's go say 4. 2.7 to the 4th power is definitely bigger than 10. If I plug that, well, this is always positive regardless. This is always positive regardless. Here, if I put natural log in there, that will be 10 minus e to the natural log of e to the 4th. Those undo each other. I'm left with 10 minus e to the 4th. That's negative. The function is decreasing. So now you could say, hey, you see this right here? It's positive, we believe you. It's continuous. You could say decreasing on what? From natural log of 10 to infinity. So natural log of 10. I'm looking on natural log of 10. Natural log of e squared, e cubed. You know what? I'll leave it as that. It doesn't matter. Let's say from natural log of 11 to infinity. Now we're safe. Now I'm going to integrate natural log of 11 to infinity of e to the x over 10 plus e to the x dx. Let u equal 10 plus e to the x. du is e to the x dx. That becomes the integral of, that is u squared du. Isn't that 1 over u? Right? Negative 1 over u. So I'm getting negative 1 over 10 plus e to the x evaluated from this number, whatever that is, to t, taking the limit as t approaches infinity. And wouldn't you say this would be the limit as t approaches infinity of negative 1 over 10 plus e to the t plus 1 over 10 plus 11. Natural log and e do each other. So if I really look at this closely, this is 0. I'm going to get 1 over 121, right? Therefore, converge by the integral test. So one thing about the integral test students don't like, you have to show that's decreasing in the event that it's not a direct, if it's not a variable only in the denominator. And the homework is right there.